Okay, that's a long formula. Is that a good formula? And what does it mean to be good for us right now? Because what is it that we want to do with this formula? Well, take a limit, but that amounts to substitution. You have to substitute that 0 instead of x everywhere. Right? Okay. Should we anticipate any problems substituting? Because I would like to check that before I keep working on the whole formula. So what can be a problem? Well, the only problem can be in the denominator. Right? If I substitute x equals 0, I will have f prime of t0, magnitude of that. That's not a problem. The numerator, well, I don't see any problem there. You just substitute and get something. What about this? Is there any problem substituting there? Well, what's the problem? The problem would be if that square root becomes 0. Can it ever become 0? No. The problem would be if the value under the square root is negative. Is that a possibility? No. So no problem. Hopefully. Unless what? Well, what is that number? That fraction. That fraction is this whole thing. And what happens when I substitute x equals 0 into that whole thing?
It's equal to
0.
Well, the fraction, not cosine inverse, but the fraction. Right? Because it's 1. So without even computing that, I know it's 1 after I substitute. So after I substitute, I will have square root of 1 plus 1 if the formula is correct. Is it correct? Wolfram alpha is supposed to differentiate cosine inverse for us. So I type differentiate arc cosine of x. Go. What do you think? Is that right?
it's 1 minus.
It's 1 minus, exactly. Oh, negative to be precise, negative 1 over 1 minus. And now it's a problem, isn't it? We were so lucky so far. But now the problem is, if I substitute, I will get 0 in denominator. And that is not allowed. So what do we do? So what does it mean? What does it mean? That I found the derivative, right? And when I substitute on that derivative, I get infinity. Well, that means that this function, the numerator function, is not good function. Is not a good function having Taylor series. So, do you have another example of a function having infinite derivative?
E to the power of x.
E to the power of x.
Yeah, e to the x.
That is a perfect function having perfect derivative at every point. right? So you have a function that has infinite derivative at some point.
1 over x.
1 over x. 1 over x is a good example. But at 0, the derivative, well, the function doesn't exist at all, right? So something like y equals cube root of x. Have you ever seen that function before? What kind of function is that? What's the derivative at 0? The tangent line is vertical. Algebraically, the derivative is infinity. The rate of change is infinite. Does it mean that function fails to satisfy Taylor series? Well, it actually fails. You can, if you try to write a Taylor series at 0, the value of the function is perfect, it's 0. But the value of derivative is infinite. So this function doesn't have Taylor series at 0. It's just not a good function. And I told you, not all the functions have Taylor series. There are exceptions, and this is one of them. It just happens rarely that you have to deal with such functions. But that rare case happened. Just happened to us. Well, remember, like, when you prepared for test and you left out a couple of problems and you thought, what are the chances? Right? Here's the chance. The function fails to satisfy Taylor series. You cannot apply the L'Hopital's rule or the Taylor series method. What do we do? Can we bypass that function? Is there any other way? Because if we go back, what we wanted here is the angle. And you told me the angle can be found using cosine inverse. And you see the derivative, well, the problem is exactly about cosine inverse. It's not about the inside function, it's about that inverse trigonometric function cosine inverse.